Hello, everyone. From near or far, wherever you're joining us today around the world, we welcome you to our webinar. Today, we will be discussing the power of digital twins and physics-informed AI for addressing acute physical climate risk. This webinar is going to be approximately 30 minutes long and is pre-recorded. However, to invite interactivity, we will be sharing a QR code to connect with us, and we will also be sharing a QR code for you to provide your feedback, your questions, your comments, remarks, so on. We want this to be interactive, insightful, leave you with wanting to find out more, starting to generate a community, but most of all, if you're going to dedicate 30 minutes of your time with us, we want this to be fun. So our agenda today is as follows. Number one, we are going to kick things off by presenting an overview of Orbyfy, what we do, why we do it, and how do we do it. Next, we're going to talk about the urgency to act. Here, we're going to discuss some stark trends around climate trajectories and the urgent need to act. Next, we're going to discuss how the regulatory environment has, of course, levers for macroscopic change and what the current onus is on federally regulated financial institutions around the world. From here, we're going to go and define the problem that banks, reinsurers, regulators, and financial services firms around the world face as it comes to addressing their portfolio exposures due to acute physical climate risk. So we're going to define the problem. From this point, we're going to delve deeper into the solution, into the realm of physics AI or first principles AI, why it's better or different than black box AI, and how it actually forms a powerful foundation for 3D climate digital twins that addresses losses and damages. This obviously ultimately gives banks, reinsurers, regulators, financial services firms with the heightened granularity to assess the true loss and damages from climate scenarios to better reflect portfolio climate adjusted value at risk. And lastly, we're going to bring it home and bring all the concepts together. And we're going to discuss a very rapid fire case study, the impacts of Hurricane Harvey in Texas. And if you'd like to go through the case study in further details, we'd be thrilled to set up a time with you and we can go through and walk through an entire demo of it. So, wherever it is you might be viewing this webinar from, before we begin, we want to get yourself acquainted with how you can reach out to us. We are building a community. We want you to reach out to us. First, you can visit our website, www.orbyfy.com. Lots of great information there. Second, connect with us on LinkedIn. You can ask questions, carry on the conversation. Of course, we'd absolutely love to hear from you. And the QR code is shown here. Or, of course, search and connect with us on LinkedIn. And lastly, we want to hear your thoughts. At any time, you can enter the following Menti code or scan this QR code to join our interactive word cloud. Also, if you click on the little icons on the bottom right-hand side of the screen, you will also see a way to go to the Q&A as well. So long story short, lots of ways to connect, but we'd absolutely love to start a community around this, and we definitely welcome your feedback. So let's begin. Let's cover off some of the basics, shall we? Let's talk about what we do, why we do it, and how do we do it. Orbyfy is a 3D climate digital twin platform that helps financial institutions manage the acute physical climate risks on their asset and loan portfolios. We create a digital twin for any city or geography in the world, capturing information about everything, whether it's buildings, structures, terrain, topography, coastal areas, proximity to bodies of water, or more. Our 3D climate digital twins help address a convolution of different climate perils, right? Including hurricanes, winds, flooding events, hail, fire, coastal erosion, and more. And I'll say this, if it obeys the laws of physics, we can do it. And ultimately, we work with banks, regulators, reinsurers to transform those climate risks into actual climate forces on building structures and homes, such that we can connect the missing chain between climate and the actual damage and loss at a far more granular scale. And why do we do it? Well, we're solving a many different problems in one, but we're solving a modeling gap problem, we're solving a junk data problem, we're solving a granularity problem. But at the end of it, not being able to accurately assess climate risks all obviously translates into real dollars and cents. It means for banks, insufficient loan loss provisions, capital adequacy issues, and reduced profitability. And today, banks, insurers, and regulators are all very much flying blind. Current risk assessment methods actually fail to capture this intricate interplay between climate events, physical infrastructure, and financial assets. And all of this, of course, is under the backdrop of evolving regulation that spells out the need for heightened scrutiny and disclosure requirements, and ultimately setting the stage for a need for a robust solution. And again, if you'd like to read more about it, check out our extensive white paper, which also can be found on our website. So, how do we do it? So, at the bottom of this slide, you see we will create a digital twin of this. And this meaning we will create city scale 3D climate digital twins to model the effects of climate scenarios on buildings, structures, and homes. And a digital twin is nothing more than a digital representation or a digital model of a physical asset, process, building, you name it. It's the most realistic or lifelike representation that you can come up with in the digital world. So I use this as an example. A few years ago, Meta was trying to push the concept of your digital avatar, the digital version of you. This is also a digital twin. And in the same way, we are trying to create the most realistic and lifelike representations of our built environment, the buildings, structures, and homes that surround us in order to simulate the effects of climate, simulate the effects of the 1 in 100-year storm event, and ultimately address what a climate scenario translates to in terms of damages and losses. So, in summary, physics informed AI that powers 3D climate digital twins so we can translate climate risks into climate forces for buildings, structures, and homes. So I promise we're going to dive much more deeper into our technology in the next sections, but the outcomes are truly powerful, right? With Orbyfy, I can create a 3D model of an entire city. Again, whether it be Boston, Brasilia, Bangkok, Berlin, Baltimore, there's a lot of B's in there. I think I've happened to live in mostly cities beginning with the letter B in my life. But wherever the city might be around the world, I can capture all the relevant information about buildings, structures, heights, building envelopes, proximities to bodies of water, terrain, topography, and simulate. Simulate what? Simulate the effects of a 1 in 100-year storm event, a hurricane, a flood, a fire, a hailstorm, an earthquake, on and on. And why? Why do we do this? Every climate event results in climate forces. And from your Physics 101, a force equals mass times acceleration, or it can be represented as a pressure times an area. But it's until and unless we understand the pressures and forces on structures and start to compare that to building codes and damage classifications, how are we ever going to get a true sense of impact? A hurricane or a major wind event translates into wind pressures on structures. A flood event or a river-based flood or a flash flood results in hydrodynamic or hydrostatic forces on a structure. A hailstorm results in point forces on a structure. So you get my point. Every climate event results in climate forces, and this continues to be the missing link today. But this is what Orbyfy solves. And ultimately, for a bank, the outputs of the digital twin are what's important. And the benefits, of course, are huge. It means for each address or postal code or at the city level, I now understand a climate scenario translated into damage categorizations and loss scores and can calculate things like probability of default, loss given default, climate adjusted value at risk, and so on. So there's a lot more details we can get into. And if you'd like to learn more, please don't hesitate to reach out. We'd love to hear from you, and we'd be more than happy to go through a demo of the full end-to-end process as well. But now that you have this overview of what we can do at Orbyfy, let's get into the webinar. The urgency to act. So before, again, we get too ahead of ourselves, let's backtrack a bit and let's discuss how did we get to this point? What's the urgency to act? And I wanted to start by asking a question. How many of you have watched the Netflix documentary Breaking Boundaries? First of all, I will say it was narrated by the great David Attenborough, which makes it a super plus for me. But if you have, you'll remember the stark warnings about tipping points. And this was the greatest insights for me when I watched this. So there are critical thresholds in the Earth's climate system beyond which changes become irreversible. And what I found interesting was the planet's temperature only stabilized something like 10,000 years ago. Before that, there would be wild fluctuations and so on. But for the past 10,000 years, we've only varied by plus or minus 1 degree Celsius. And this period of stabilization even has a name. It's called the Holocene. But we are collectively risking reaching a tipping point. And if we do, we would enter a period called the Anthropocene. The flourishing of human civilization, actually, if you think about it, has been predicated on this period of weather stability, this plus minus 1 degrees. But if we face erratic weather trends, the question is, what does it mean for all of us? So, 2023 was sadly the warmest year on record since global records began in 1850. The global average temperature was 1.48 degrees C above pre industrial levels. General weather trends, of course, are getting worse. And I can almost guarantee that wherever you're viewing this from this week, there is likely a major weather event making the news, right? Heat wave intensity has increased by 25%. Flood intensity has increased by 40%. Hurricane intensity has increased by 23%. It's all an increase. And what this means is global insured losses from natural disasters are projected to reach $180 billion annually by 2030, with a significant portion impacting properties financed by banks. But moreover, it affects everyone in terms of not being able to get insurance for your home or higher insurance rates. I recently read a paper published by the University of Exeter in the UK, and it was aptly called Climate Scorpion, right? The sting in the tail. And it brought up an interesting concept around the risk of total ruin, or the point beyond which our global society can no longer successfully adapt to climate. And they also posit in this paper that we should collectively think about planetary solvency. And I thought that this was quite important, right? How does the world collaborate to solve this challenge using all the levers we can, technology, regulation, and more? And in the end, this is also personal. We all started Orbyfy because we wanted to be a part of the solution. And if my life's work is dedicated to all of this, all the better. Regulatory environment. So let's speak a little bit more about one lever for change, and that's regulation. In the past few years, we've witnessed an unprecedented surge in climate related regulations. Since 1997, there's been a 20-fold increase in the number of global climate laws. And if you want to see the climate regulations where you live, you can. And if you check out the database that the Grantham Research Institute with the London School of Economics has put together, you can actually go in and see the number of laws and policies and regulations all related to climate by each country in a quite cool and interactive map. And we've also written more about this in our white paper, which highlights the differences between countries and regions like Europe versus, the US and Canada. The ISSB's landmark IFRS S2 standard has set a global benchmark for climate-related disclosures. So this then ignited a domino effect. Countries like Canada with OSFI's guideline B15 are swiftly aligning with the ISSB. However, the European Union's EBA is taking, I would say, a more nuanced approach, focusing on physical risk assessments. And then, of course, across the Atlantic and coming back, the SEC is finalizing its climate disclosure rules. So it's clear that a one-size-fits-all approach doesn't exist, and we're seeing a patchwork of regulations, each with its own nuances and complexities. And this creates a significant challenge for financial institutions that operate across borders. But this regulatory evolution presents both challenges and opportunities. So on the one hand, this increased scrutiny and disclosure requirements demand significant, resources and expertise. And on the other hand, those who can effectively manage climate risks can gain a competitive advantage and build trust with stakeholders. And this is where Orbyfy fits in. The regulators are creating initial climate disclosure frameworks. The banks, insurers, and financial services companies are responding, and the uncertain gap in between is where Orbyfy can help to provide greater clarity, granularity, and simulate different scenarios, all via 3D climate digital twins. Defining the problem. So, what's the problem in modeling climate? Traditional modeling approaches for physical climate risk assessments, they rely heavily on historical data sets. However, it's the question of junk data in and junk data out. The increasing severity and frequency of physical climate events, they pose a challenge. Accurately incorporating these future risks into traditional models, they prove difficult, if not infeasible, right? And with Orbyfy, it's possible to actually decouple the risk assessment model from its historical data dependency. A recent evaluation from the Bank of England's Climate Risk Stress Test, the CBES, revealed a significant data and modeling gap that actually hindered accurate assessments of physical climate threats. So, a lot of the participants all said the same thing, which is over 70% of financial sector participants identified and said that modeling these risks are the biggest challenge. And they, of course, highlight the nascent state of expertise in the area. And then this is despite the Bank of England providing substantial data. And with that, 75% of firms relied on additional third party data and models to actually complete the exercise. So, this reliance on external support, with 70% seeking data and modeling assistance, it underscores, quite frankly, the limitations of data. And the consequences of this data shortfall are also stark. The potential underestimation of future financial impact. So, studies then suggest that these modeling gaps could lead to bank impairment rates 40% higher than reported for mortgages and wholesale loans, and for the UK, potentially quadrupling UK insurance losses, which come primarily from intensified flooding. So these findings paint actually a clear picture. Robust data and sophisticated modeling techniques are definitely needed and are crucial for a more accurate and holistic understanding of climate-related financial risks. But with Orbyfy, again, we provide these solutions to these problems. Whether it's a modeling gap problem, the junk data problem, the granularity problem, all of these and all the other problems that you see here on the screen, this is what we solve for. And the results with Orbyfy speak for themselves. Reducing modeling costs, gaining modeling uplift, enhanced portfolio-wide risk analysis, but ultimately reduce loan default rates, improve capital adequacy ratios, reduce loss scenarios, and establishing, more importantly, a robust framework for regulatory compliance for acute physical climate risk. So now we have a good background, and now that we've kind of gone through a lot of things, let's move on to some of the cool topics. And this is my absolute favorite part to talk about because it's so much fun, and it also because it holds a special place in my career. In my first job as an engineer, I got to do some incredibly cool things. Very, very grateful. I got to do R&D, real engine testing, all sorts of stuff. But one of the things I got to do was create digital twins and get digital twins of this, digital twins of a gas turbine. Back in the day, we didn't call them digital twins. We called them CFD simulations, but the principles are the same, even though the concept now has evolved with the help of AI. The point of the story is that 2 decades ago, I feel like we didn't really live in a world of buzzwords. Digital twins, IoT, and AI, I mean, these are the things I did 20 years ago, even though we never used such terms. And the other point of the story is, with the pace of technology as rapid as it is, it takes its root in very established concepts. And the more you dig in behind buzzwords, you'll learn it's not as complicated as it might seem, on the surface. And I think this applies to the concept of digital twins too. And as I mentioned before, a digital twin is nothing more than the digital representation of the physical, whether that physical be an asset, a system, a network, a process, a building, whatever it is. And digital twins can have different levels of complexity as well. I would say the most complex digital twins can precisely simulate reality in a reactive, real time, bidirectional, synchronous, high fidelity, closed feedback loop process. And I think the closest thing I can think of in terms of models out there in the real world that are actually being used and that can, reach this level of simulating and reacting to reality might be something like Tesla's self-driving features, if you will. This is also the type of stuff that is possible with solutions like NVIDIA's Omniverse, so creating digital twins of entire, manufacturing facilities, if you will. So a digital twin is nothing more than a digital representation of the physical. But the means of how you encode the digital twin is important. What about the underlying model of the digital twin? Much of today's AI is what I would call black box AI. Data goes in, data gets transformed by neural layers and activations that create these neural networks, and data comes out. But the link between inputs and outputs can't be explained. And that's the explainability gap that we have. But the branch of physics informed AI or first principles AI says, let's not use this black box. Let's actually start to encode the digital twin with the actual physics of the systems. And that means the set of equations that govern the object. So, where is this all going? And where is AI going? Well, these days, I would ask, where is it not going? If you follow what's happening in the stock market these days, stock valuations are now being increasingly tied to a company's AI abilities. The era of chips and semiconductor manufacturing related to GPUs and data centers is exploding. We have ChatGPT and OpenAI and large language models being injected everywhere. So it's exciting. But I would like to take a look at the Gartner AI curve, which is always a good marker to see the state of AI in general terms, in terms of where it is on the hype cycle, and if you can take a look at the leading edge right now, what do you see? And it's kind of circled on this chart, but it's first principles AI. It's also called, again, physics informed AI. And first principles AI is an approach to developing artificial intelligence systems that begins with breaking down complex problems into their fundamental components, right? It involves by starting with the basic truths or axioms and building upwards rather than relying on existing models or assumptions. So there's a few key characteristics that I think are important to highlight here with respect to first principles AI or physics informed AI, which are there's a focus on fundamentals. You want to identify the core principles underlying the problem. It's also building from the ground up. It's constructing solutions based on these foundational elements. There is actually a reduced reliance on data. It's back in the day, the more data that you would chuck into a machine learning algorithm, eventually it's the law of large data sets. They all kind of converge. But this means there's actually less dependence on large data sets compared to traditional machine learning. Potential for greater explainability. Since the models are actually built on first principles, their outputs are easier to understand and the outputs are more reliable in the application in complex domains. So again, it's useful for complex problems as we see in the world of climate risks and modeling those climate risks. And of course, for climate and modeling the impacts and damages from climate, this becomes incredibly important. Using the physics of the natural phenomenon, which are governed by the conservation of mass, the conservation of momentum, the conservation of energy. These are all equations, right? The Navier-Stokes equations, if you will. Modeling and capturing the physics of hurricanes, floods, fires, hailstorms, you name it. And when you start to encode this and encode the impacts on building structures and homes, that's when we arrive at 3D climate digital twins. And if you think of that these 3D climate digital twins are new, or, it's a nascent area, I will say to you the technology is absolutely not. That's what I said at the beginning. I've been doing this for 20 years. The first large-scale global digital twins were actually developed as early as the 1950s. Scientists began to develop the digital twin of the Earth, so computer models that replicate the planet's, climate systems using the fundamental laws of physics. Scientists then just discretized the Earth into a 3D grid. They applied the core principles of physics, fluid motion, and chemistry to each individual cell. And within each grid, atmospheric models then calculate wind patterns, heat transfer, radiation levels, humidity, surface water interactions, right? So this has been done for a very long time. And these sophisticated digital twins of the Earth aren't some sort of future focused tools. They are at the very foundation of our everyday weather forecasts. And this is exactly how you get your weather forecasts on your phone today. And these same physics-based methodologies used at a global scale for modeling climate, this is what we do concerted into a city scale, and using AI to power this and power the scale factor of it. So this is what powers Orbyfy's 3D climate digital twins, again, which translate climate risks into climate forces and damages to truly understand climate impacts on buildings, structures, and homes. So, without going on and on, let's finish this webinar with what I would call an absolutely rapid fire case study. And we won't have enough time to go into a demo or an end-to-end demo, but for that, I would say please, please, please do connect with us. We would love to set up a time with you, your team, your group, whoever, to discuss further about the capabilities of our technology and a demonstration of our platform and how we can customize and adapt our platform to your needs. So please do connect. And if you connect with us, we would love to take you through this case study for Hurricane Harvey. We can go into more of the details around the losses and the damages, and how we start by taking map data and information, how we capture the 3D data of buildings and structures and homes, how we convert that 3D data into 3D models, how we discretize the 3D city scale models and set up the models for various climate perils. What are the modeling outputs in terms of climate forces and damages, the range of geographical outputs, and ultimately the types of dashboards that are helpful to banks, reinsurers, and financial services firms and regulators, and the different types of climate KPIs that are possible, as well as how we visualize this risk in a platform that can be connected to you. So as you can see, the story is far from done. And we've tried to fit in as much as we possibly could into this short webinar to give you a bit of an introduction. But again, please do connect with us. Whether it be on LinkedIn or joining our word cloud, please do set up a meeting with us. We'd absolutely love to hear from you. And again, thank you for your time. And until we meet again, thank you.